a connection between partial symmetry and inverse procedural modeling. Our paper examines the following question. Given an example model, shown in red here, can we derive a set of rules how to build new models that are similar to this exemplar? In our case, similarity means that each part of the newly created object is taken from the original. If we match neighborhoods of radius r, we obtain an object that is r similar. How can we construct such objects? Here is an illustration of our main idea. This image shows two slightly different windows. If we can find a cut through a symmetric area that separates the variations from the rest of the model, we can replace the resulting pieces. We obtain an altered image that is similar to the original. We call these boundary curves docking sites and the cutout pieces dockers. By using a larger boundary of thickness r, we obtain r-similar pieces. Now we have to systematically construct such docking sites. This is done by looking at the partial symmetries of the input exemplar. In this example, the red area is symmetric to the blue area under a translation. We can cut through the red area and thereby through the blue area as well, such that the model is split into two disconnected pieces. These pieces can then be recombined to give different results. Obviously, it does not really matter where exactly the cut line is located within the symmetric area. The result will be the same. Therefore, we always use the boundaries of the symmetric area. However, not every boundary curve is a valid docking site. Let us look at this example of a more complex topology. The red line cuts the model into two pieces, but the resulting blue line fails to do so. Therefore, we need an algorithm to compute valid docking sites automatically. Our algorithm starts by identifying continuous non-symmetric area. Let us call these pieces red 1, 2 and 3 for the source site, and blue 1, 2, 3 for the target site, which is the site where the symmetry transform maps to. Now we build a graph of these pieces. Our goal is to connect the minimum number of pieces that need to be combined such that the red and the blue cuts are valid docking sites, meaning such that the model is cut into two pieces for the red and blue side simultaneously. As a first step, we connect red and blue pieces whenever they share a common boundary. For example, the boundary of red 1 maps to the boundary of blue 1 under the symmetry transformation. Therefore, we connect them by an edge. Looking at blue 1, we find out that it also shares a symmetry boundary with red 2. Therefore, we connect these two as well. We now do this for all the remaining pieces and obtain a graph of dependent boundaries. In this graph, we now compute the connected components. Each connected component represents a valid pair of red and blue docking sites, and red and blue dockers. These docking sites are elementary. All other possible valid combinations can be built from them. Finally, we build a shape grammar. We compute docking sites and dockers for all salient symmetries in the object and examine their hierarchical interdependence. This yields a context-free grammar that describes a space of objects that are all r-similar to the input exemplar. Here's an example grammar. We start with a white docking site, which is the root of the shape grammar. We then choose among dockers that match the docking sites of this piece. We continue recursively until all pieces are closed by terminal docking sites. Finally, we show some results obtained with our method. This is again the castle example from the beginning. And these are a number of variations created from random instantiation of our shape grammar. And this is a grammar our algorithm has computed for this example. This bus station example has been created by interactively instantiating rules from the grammar. And this example shows a large random variation of a playground scene. This is a parking structure being resized in 2 dimensions, using specialized grid replication rules. For details how these work, please refer to the paper. Similarly, this example shows how a spiral staircase is adjusted in height. The algorithm correctly identifies the helical motion of the instantiation pattern. This example shows shape variations of the new town hall in Hanover, which has been acquired using a 3D laser scanner. Our implementation is able to handle such real-world datasets with noise, holes and outliers robustly. The following footage shows a screen capture recording of our interactive modeling tool. The user starts with a base model and, hovering over the scene, the editor displays docking sites. For each docking site, the system computes a list of suggestions of geometry that can be plugged into these sites. Using this tool, the user can very easily create variations of the exemplar shape in the form he or she desires. For this final example, we have used the model of a space station as input exemplar and created a random variation. This concludes our video. Thanks a lot for your attention.